Hello, and welcome to Empowered Learning. This particular video will be about the basic logarithmic rules, as well as basic logarithmic properties, and using those properties to be able to do such things as reduce logarithmic expressions, as well as expand out logarithmic expressions. So we want to start off with talking about what we call the change of base rule. And so the change of base rule is a rule that gives us a way to be able to um, rewrite a logarithm in any base to convert it to any other base. So as an example here, if you see I have log base 5 of 31. Now, you may not know exactly what that number is. As a matter of fact, no one does because it's an irrational number. However, depending on what kind of calculator you have, you may not be able to type in log base 5 of 31 directly. Okay. In the event that you have a calculator that does not allow you to be able to type in logarithms of base other than base 10 and base e, we use the change of base formula to be able to convert from any one base to the other. And so simply put, if we go back up here, we see that changing from log base A to log base B entails us saying that we want to do log of B, and then whatever the logarithm function is being evaluated by, which is what's inside the parentheses, goes on top, the base goes on bottom. So let me get rid of this part here, and this base goes on bottom. Okay, so in essence, when I'm talking about log base 5 of 31, if we want to change to log base 10, of course we say log base 10, or simply we could just not write the 10 at all, and just log of 31 would be log base 10 of 31. So see, the 31 goes up, 5 goes down, and we're done. And so that's essentially what this means here. Okay. Now, please note that we can change from any one base to any other base, and we still end up with the same thing. So my point in saying that is I could also change from, let's say, log base 5 to log base 8, or log base 5 to log base e, which is the natural log, or log base 5 to log base 16. I can do all those things. Okay, so log base 5 of 31, an equivalent way of writing it is log of 31 divided by log of 5. And when we do this, we get an answer that is approximately equal to 2.1336. Okay, and so in this particular example, what we did is we changed the base from base 5 to base 10. For our next example, you see that we have log base 4 of 103. And so if I wanted to change that to log base E, which is another way of saying it would be natural log, or the ln here, then again, 103 goes on top, 4 goes on bottom, and we just tell ourselves to do natural log. Okay, and so in this instance, if we put this in our calculator, we would see that we end up getting 3.3432. So that's approximately, oh, sorry, that's not right. So it should be 3 point, still did that wrong. So let's try that again. Should be 3.3432, like that. So that is what the answer would be to that if we put it in our calculator. And so again, in this example, we went from base 4 to base E. Okay. And so now we turn the tides here a little bit and start to talk about some other properties. So just like how we had the property when we talked about exponents in an earlier video, that if we have an exponential equation where the bases are the same, then that concludes that the exponents must be the same as well. We sort of have the same thing going on with the logarithms. Okay, so we know that this property here goes this way, saying if we have the equation where we have two exponential expressions, bases are the same, then the exponents are the same, and it also goes the other way, okay? Meaning that if we have two things that are equal, we can form an exponential equation by saying whatever we want as the base, we let it be the base on the both sides of the equation, and let the things that were equal be exponents. Or put another way, if the exponents are the same, then that means the bases must be the same too. So doing it like this double arrow here is representative of a biconditional statement, meaning that if A is equal to B is true, then log base B of A is equal to log base B of big B. And going the other way, if log of A equals log of B is true, then A is equal to B. So in general, whenever we see two things being equal and then we put log, apply the log function on both of those, what we call this is the log of both sides theorem. And this is where we get for an equation taking the log of both sides, if you've ever heard of that before. Okay. So similar to the exponential, where we can make an equation an exponential equation, we can take a regular equation and make it a logarithmic equation as well by this particular rule. So now what we're going to do is do some more practice in changing an equation in exponential form to logarithmic form. Okay. And so here we see that in exponential form we have 9 is equal to 3 squared. And of course, we remember from the previous video that we watched that logarithmic form would be like this. Exponential form is like this. So here, for this first one here, we know that 3 is our base, so that's always A, and 2 is Y, so that'll always be our exponent. So we have Y log base A of X. And so we know that 2 is Y, 3 is A, and X is going to be 9, okay? So if we move on to example B, we see that W is our exponent. And remember, the logarithm is nothing more than a fancy way of expressing the exponent. So we say the exponent is equal to log of base 3, which is equal to log base 3 of 4.6. And of course, we can always go back and test to see if what we converted is correctly just by going A raised to the Y equals X. Again, A raised to the Y is equal to X. So if we follow that, 3 raised to the W is equal to 4.6. And we see that's exactly what we get here. Moving on to example C, we see that E raised to the 2.2 equals M ends up equaling 2.2 equals log base E of M, and log base E could be written abbreviated as natural log, or ln of M. Example D, Z raised to the third power equals to 2.1. We know 3 is the exponent, so that would have to be what Y is. Z is the base, and of course 2.1 is what's on the inside. So now we'll work on these 4 examples here to get some practice. So here we know that 7 is the base, Z is the exponent, and Z is the exponent, and 49 is going to be what's going to be on the inside there. So need to erase that and put a Z. Sorry, not a Z, but an X. So here that means Y is equal to log base A of X. which means z is equal to log base 7 of 49. Okay. And so, of course, if we were solving that, we'll see later on that the actual answer to this would be 2, because we know 7 raised to the second power is 49. But for right now, we're just asked to convert from one form of the equation to the other. Okay. For the next one, the exponent is a -3. We have log base 4, and we're going to evaluate the log at 1/64. For the next one, we know 3 is the exponent, the base is 5, and we're evaluating log at 125. And of course, for the last one, -4 is the exponent, the base is 2, and we evaluate that at 1/16. Okay, so that's how we do the conversion from an exponential equation to a logarithmic one. Okay, so now we're going to go the other way and change logarithmic equation into an exponential. So we see that for example A, we can just say 3 raised to the power of -2 is equal to 1/9, or A raised to the power of y is equal to x. So that's how we get 3 raised to the -2 is 1/9. For example B, z raised to the power of 2 is equal to 4. Okay. For the next one, 2 raised to the power of c equals 6. And we see 2 raised to the power of 10 is equal to z. So that's how we convert those. If we move on to our next set of examples here, we see that 10 raised to the 3 is equal to 1,000, and w raised to the y is equal to x. Okay, and so for g, we know that a raised to the y is equal to 15. And of course, for this last one here, and this is actually another property that we're going to learn here as we move ahead, we know that e raised to the power of 1 is equal to e. And of course, we know that's true because for any base a, we know that anything raised to the anything raised to the power of 1 is just itself. So now we are going to talk about the properties of a logarithm. Normally in a course, when you first learn these logarithmic properties, it's usually told to you that you need to just memorize them and use them accordingly. What I am going to do here is spend some time to try to get you to understand what these actual properties are trying to communicate to you, okay? And then after that, we'll go and do some examples. So for those of you that kind of already understand what is going on here and you just want to see how you use it, you can go ahead and fast forward the video. For those of you that, for whatever reason, don't care to really know that minute information right now, you can fast forward the video to the examples. Okay. All right. So for property 1, I guess for all these properties rather, what the logarithmic property is trying to communicate is the same thing as what it communicates in the exponential world. And so what I mean by that, I'll just use this first example here. So we know from our exponential rules that a raised to the 0 is equal to 1, meaning anything raised to the 0 power is equal to 1. Well, it turns out that property 1 is just the logarithmic equivalent of saying anything raised to the 0 power is equal to 1, because a raised to the power of 0 equals 1. Okay, and in essence, that's what all of these logarithmic properties are doing. It's something that we already know in the exponential world, and so we're just translating it if we needed to write our exponential equation as a logarithmic one. Okay, so we know that for property 1, this is the same as just saying anything raised to the 0 power is 1. For property 2, log base a of a is equal to 1. we know that that's the same thing as saying anything raised to the power of 1 is just that anything. Okay. Property 3 says log base a of a raised to the x. So this is when we have log of something raised to an exponent. We know that the answer to that is the exponent. And of course that makes sense because we want, anytime we talk about a logarithm, the answer to that has to be the exponent of an exponential function. And so here we use our definition of a logarithm. We know that a raised to the x is definitely has to equal a raised to the x. Okay, and so we are in particularly talking about that a right there that x that I have circled right there. Okay, for property 4 actually comes from knowing this property that y is equal to log base a of x, and I'll try that again here. Y is equal to log base a of x, and that can be converted to a raised to the y equals x. And so if you remember that log base a of x is just a fancy way of expressing an exponent, you see that this y that's right here is equal to everything we see here, the log base a of x. So here we could really think of this as a raised to the y equals x if y is log base a of x. So again, we see that property that we've already studied, if we convert that in the opposite kind of way, in this case, if we convert it in the exponential type way, we see that we get an answer of x as a result. Okay. For property number 5, what property number 5 is alluding to is what happens when we have an exponential expression of one base being multiplied an exponential expression of the same base, but the exponents are different. In this case, we know that we can add the exponents. So here, what's going on with log base a of m times n equaling log base a of m plus log base a of n makes sense because we know that log base a of m is an exponent of some exponential expression or function. Log base a of n is also an exponent. So here you see we're adding exponents there. Here you're seeing that we're multiplying, and we're multiplying here. Okay, so again, this just means we're taking the exponential rule that we see here and translating it into logarithmic form. Okay, so I'm going to erase this, and then you can kind of guess that if property 5 is talking about how do we write multiplying two exponential functions that have the same base, or two exponential expressions, whether they have the same base, by adding them, then property 6 deals with what happens when we divide two exponential expressions that have the same base. So this is the exponent equivalent of that. And of course, you see the subtraction here, subtraction here. You see the division here and a division there. Okay. What property 7 alludes to is taking a situation where you basically have property 5 and you have, instead of m times n, and assuming that m and n are different, you have a situation where you have just log base a of m times m times m times m times m. And so to write that out, let's say if we had log base a of m times m times, and we just keep on multiplying m times itself a number of p times. Okay, so let's say we did that p times. Then of course this would be log base a of m plus log base a of m And then we just keep on going until we get to the last log base A of M. Okay? And so if we did this P times, then we would have, if we count all the log base M's that we would have P of them. Okay? So we know the definition of multiplication is just repetitive addition. So if we're adding log base A of M to itself P times, then that ends up being P times log base A of M. So that's where that actually comes from. Out of all the properties, to me, this is probably the one that is most important, because this is the one that you will use most often whenever you're solving a exponential or logarithmic type of equation where you're dealing with expressions that have different bases. So essentially what this allows you to do is be able to take something that's raised to a power, and if your variable is in the power, then you can take the exponent and basically pull it out and thus multiply it times everything else. Okay, and so then from that point, if you need to solve for, let's say, P in this case, and P is in the exponent, by having M raised to the P inside of a logarithmic function, we're allowed to pull that P out and multiply it, thus being able to solve for P there. Okay, so properties 1, 2, 3, 4, 5, 6, and 7 all sort of give the flip side story to the exponential rules that you already know. If you're probably watching this, you already know those, or at least heard of those. We see what those exponential rules look like from a logarithmic perspective. Okay. Of course, property 8, it says basically the same thing that we talked about earlier, and I'll go back to that particular area so that you can see that. So here, when we said that if A is equal to B, that is true if and only if, that's what that double arrow means, if and only if log base B of A is equal to log base B of big B. Okay, and of course this goes along with the log of both sides theorem. If we go back to property 8, we're essentially saying the same thing. It's just that I wrote it with a different base, and this should be base A, not base B. So for those of you that actually have this printout, replace that B there for the base with an A, because the bases have to be the same in all these in order to use these logarithmic properties. Okay. Okay, so let's move on down, and we see that for special cases here, property 9 is natural log of E is equal to 1. Okay, and so I want to talk about that for a second. So I'm going to erase some of the stuff up here. Natural log, if you remember, is just log base E. So property 9, log base E of E is equal to 1. So if you look at that, this is essentially saying the same thing that property 2 is saying if our base A is now equal to the irrational number E. So property 9 is just a specific case of property number 2. Okay. Natural log of 1 equaling 0 could be rewritten as log of E, log base E of 1 equals 0. And if you look, that is a special case of property 1 when the base is the irrational number E. Property 11 is same as log base 10 of 1 is equal to 0. And so, of course, that's the same as property 1, special case of when the base is 10. And, of course, here, for property 12, we know that log base 10 of 10 is equal to 1. That is a special case of property 2 when the base is 10. And for property 13 is just the change of base rule. Okay? So here we see that we have all these properties, and now what we're going to see is how to use them. So in my first two examples, we have a logarithmic expression that is what I like to call in a compact form. And what we want to do is expand out this particular logarithm using the sum, or expand it out into a sum or difference of logarithms. Okay. So if we note here, we know that log base 5 of 25x looks a lot like log base a of m times n. And we know that because of that, we can rewrite it as two separate logarithms. So here we know that log base 5 of 25x is just log base 5 of 25 plus log base 5 of x. So we're just following this particular property here. Now, for log base 5 of 25, you know that 25 can be written as 5 squared, okay? And then from that point, if you look back up, we know that log base 5 of 5 squared sort of fits the same profile as far as the rules and properties are concerned as property number 3 here, okay? And so property number 3 says that log of anything greater than anything to another power, the answer to that is just going to be that power. And so here we see that log base 5 of 5 squared is just 2, okay? Now, one thing I want to point out is that we also could look at log base 5 of 5 squared by looking at property number 7, okay? So property number 7 basically tells us that if we have log of something, log base a of something raised to a power, we can take that power and pull it out. And so it doesn't matter whether the base for the actual logarithm here and the base for the exponent that's inside the logarithm are the same or not, okay? This still applies. So because of that, I could have looked at this and said, let's pull out the 2, and then now let that be 2 times log base 5 of 5, okay? So we look at it that way. And then from that point, we see that log base 5 of 5, if we go back to our properties, looks a lot like property number 2, which is log base a of a is equal to 1. So hence here we know that log base 5 of 5, all that is 1, and 2 times 1 is 2. So that's how we get that answer there. The log base 5 of x, that's after the addition sign here, there's nothing else that we can really do with that, so we just have to leave it as is. So for example B, we see that we have a natural log of 1 divided by e, and if you notice, this sort of fits the profile of property 6, okay? So with property 6, we see that natural log of 1 over e can be rewritten as natural log of 1 minus natural log of e. We know that natural log of 1 is equal to 0, and so we know that because of property 10 right here. We also know that natural log of e is equal to 1 because of property number 9. So once we do that, we write in what we know, and then we see that our answer ends up being a -1 in this case. All right, so on next set of examples here, we're going to expand this out. So we know that we have 17 times z inside the logarithm. So we're going to rewrite this as log base 7 of 17 plus log base 7 of z. And since 17 is prime and it cannot be written as 7 raised to some power, this is all that we can do with that example there. For example D, we see that we have log base 9 of 11 times 10. And so 11 times 10 inside the logarithm can be rewritten as log base 9 of 11 plus log base 9 of 10. Moving on to our last two examples here for expanding out. We see that natural log of C times D can be rewritten as natural log of C plus natural log of D. And for example F, we see that natural log of X divided by e to the X is natural log of X minus natural log of e to the X via property 6. Now from here, one of the things that we can note here is that natural log of e to the X is just like saying log base e of e to the X. And we know from, I believe it's property 3, that log base e of e raised to the X is just X. And so from there, we see our final answer is just natural log of X minus X. So we've done a situation where we have a logarithmic expression in its compact form and we want to expand it out. So what we're going to do now is take our logarithmic expressions and express them as a product, okay, meaning something times something else. And this is mainly to exercise property number 7. So here we see we have log base 7 of x raised to the 5, so we can pull the 5 out. And so that ends up being 5 times log base 7 of x. Okay, for our second example, same thing. We have log base p of t raised to the 5. And of course, we could just pull the 5 out. And we see that this is going to be 5 times log base p of t. And then for example C, we can pull the y out of the exponent, and this will be y times log base w of 2. Okay. And then of course for D, it's already worked out here. We see property 7 rewritten again, so we just take the 100, pull it out, and we see that that would be just 100 times log base 3 of w. And again, we're not trying to solve for x or t or w or y. All we're trying to do at this point is be able to take a logarithmic expression and write it as a product of two things. And what we did before then was take a logarithmic expression and expand it out as a sum or difference of logarithms. Okay. So now what we're going to do is take it in reverse, and instead of taking a single logarithm and expanding it out into a sum or difference of several logarithms, we're now going to take a sum or difference of several logarithms and now roll it in or make it in its compact form. Okay, and so here we're going to be using mainly properties 5, 6, and 7 from earlier. We're just going to be using the other side of it. Okay. So for example, for A, we know that log base A of m divided by n is just log base A of m minus log base A of n, where m in this case would be the 100 and n in this case would be 10. So we need to change it from this form, which is on the right, to this compact form, which is on the left. Okay, so in using that, we know that log of 100 minus log of 10 is going to be the same as log of 100 divided by 10, which is just log of 10. And remember that log of 10 is the same as log base 10 of 10. And from some of our earlier properties, we know that log base 10 of 10 is 1. Okay. For example 2, we see that we have subtraction and we have addition. So I am going to go ahead and just go from left to right. So we see here that natural log of x minus natural log of y can be rewritten as natural log of x divided by y. And then we have plus natural log of z. And then from here, we'll use property 5 which is log base A of m times n is equal to log base A of m plus log base A of n. And we're going to multiply the quotient x divided by y and z together. So if we do that, this is what the result would be. And since z is the same thing as z over 1, you could rewrite it this way as well. So either one of these two answers is correct. All right, so moving on to our next example here. We see that we have natural log of x raised to the 6 minus 3 times natural log of the cube root of x squared, okay? So the first thing that we want to do is try to simplify this part as much as we can. And so one good thing that we could do is we could rewrite the cube root of x squared as just x raised to the 2/3, okay? And so now from here, we know that from property 7, we have 3 times natural log of x raised to the 2/3. That would be the same. That would be the same here if we took this 3 and put it back in the exponent. This would be natural log of x raised to the 2/3 times 3, okay? And we know 2/3 times 3 is just x squared. Yeah. Let's get rid of that. So that would just be x squared. And then from that point, we know that natural log of something minus natural log of something else can be rewritten as natural log of that something divided by the something else. And of course, x raised to the 6 divided by x raised to the 2 just ends up being x raised to the 4. And so natural log of x raised to the 4 would be the simplest form that c could be in. Okay, so I'm going to try to move this answer here and put natural log of x raised to the 4 there so I can have some room to work this last example. Okay, so here for D, the first thing that we're going to do is take this 2 and put it back as an exponent here. And we also notice that log base 3 of 3, since the base and what's on the inside is the same, that's going to equal 1. So this will be log base 3 of x squared plus log base 3 of 5 minus x. And so here we see that we have log of something plus log of something else. So our property 5 tells us that we can multiply these two things together. Okay, and so we could either leave the answer like this, or if it makes you feel better on the inside, you can go ahead and multiply distribute the x squared to both terms. If you do that, you will be getting this as an answer. And if you notice, I'm using brackets here. No big difference in between that and the parentheses. I just decided to use brackets here. I could very well just write parentheses here and here and here and here, and that would mean the same thing. All right, so now what we want to do is take a single logarithm and expand it out. But this example here is showcased because it's a little bit more difficult of an example. We have a lot of things going on here, but I wanted to talk through it just so that you can get an idea of how to tackle it. Okay, so we have log base 10 of x cubed times square root of x plus 1 divided by x minus 2 quantity squared. Okay, So the first thing that we notice is we have log base 10 of something divided by something else. So our property 6 allows us to be able to rewrite it this way. Okay. From that point, we realize that this first term here can be broken up into two terms, because we know log of something times something else is the same as log of that something plus log of something else. So that's what you see here and here. Minus log of x minus 2 quantity squared. The x minus 2 altogether acts as a single base. So the only thing that we can do here is pull this 2 out via property 7. So that's why you see the 2 there. Okay. So from that point, we're just going to work on this term and this term to get it expanded out as much as possible. So first thing we know here is that we have x raised to the 3. We know that we can take this 3 and pull it out via property 7. So that's what you see here. And we know that square root of anything is that same anything raised to the 1/2. So this is what you see here. And of course, the minus 2 log of x minus 2 still stays the same. And of course, the last thing that we do here now is take the 1/2 and pull it out of the logarithm. So we have that there. Everything else is the same. And this is what the expanded form of our logarithmic expression here would look like. Okay. Now, the purpose of doing all this, just to kind of give you some insight on why we do this, is that depending on what course you're in, you may be studying how to solve logarithmic equations. And so we use these properties to be able to either contract or expand a logarithmic expression so that we could solve for a variable if need be. Sometimes it is a need for us to take the form that we have here and make it as compact as possible on one side before we start to solve for x. At other times, we need to expand it out to be able to find out where x actually is so that we can single out those terms and try to solve for x or the variable there. Okay, so that's why we're doing this. All right, so let's move on to the next example here. So we see that we're going to rewrite, use properties of laws to rewrite the expression as a sum or difference of logarithms. So we're going to basically expand this out. So this will be log base c of x raised to the 8th plus log base c of y raised to the 5th plus log base c of z. Okay, and we're doing that because all three things on the inside of the logarithm being multiplied times each other. Okay, so from this point, we have the 8 that can be pulled out via property 7, 5 that can be pulled out via property 7. So if I have that, that'll be 8 times log base c of x plus 5 log base c of y, and then just log base c of z. And of course, at this point, that will be all you need to do. For example B, sort of the same thing. We have a little bit more involved, but if we just take it step by step, there's no problem there. So we start off, we see that we have log base m of square root of 5r cubed divided by z to the 5th. And so we know that anytime we say square root of anything, that's the same as that anything raised to the 1/2. So we rewrite what's inside the logarithm as just all this stuff raised to the 1/2. And then from that point, we can pull the 1/2 out via property 7. That's what you see here. Okay. From this instance, we know we have 1/2 times all of this. And so since we have log base m of something divided by something else, we know that via property 6, we can rewrite log base m of something divided by something else as log base m of something divided by log base m, minus log base m of something else. Okay, So we looking at this as the m, and that's the n, then this is the m, and that is the n. Okay. So from this point, we know that we can take this 5 and pull it out. Okay. And we also know that since we have 5 times r cubed here, we can split up this term into 2 separate terms, namely log base m of 5 plus log base m of r cubed. And then if we pull out the 5 via property 7 out of the last term's exponent, we just have 5 times log base m of z. Okay. And then from that point, the last thing that we can do here to expand everything out is take the r cubed and take the 3 and just pull that out. And so we see we have that there. And so now, if we simplify everything, we have 1/2 times log base m of 5 plus 3 times log base m of r minus 5 times log base m of z. And if we distribute our 1/2 to all terms, this is what our answer ends up looking like. Okay. All right, so for example C, we're going to do similar. So we're going to start off by noting that since we have log base 5 of something divided by something else, we're going to use property 6 to rewrite. And then from here, we see that 5 root 7 is the same as 5 times square root of 7. So we're going to rewrite this as log base 5 of 5 plus log base 5 of square root of 7 minus log base 5 of 3. Okay. And then of course from there, if we keep on going here, we'll see that log base 5 of 5, all this is just 1. Okay, and we know that from one of the earlier properties. So here, this would just be equal 1. We know that square root of 7 could be rewritten as 7 raised to the 1/2. And then we just have log base 5 of 3. So now to finish it up, we know that we can pull the 1/2 out. So that would be 1 plus 1/2 log base 5 of 7 minus log base 5 of 3. And this would be the answer to this expression here in expanded form. Okay, so for our last set of examples here, we're just exercising the properties of log base a of a raised to some power is that power, as well as the a raised to the log base a of x equaling x here. So, and the purpose of these assignments is to let you know the bases just don't have to be numbers. They could be numbers, letters, numbers and letters, expressions, whatever. The number is not as important as the place where the number or the expression is. Okay, so here we see that we have log of base 3x, log base 3x of 3x, that will equal 1. Okay, and that's following this particular property here. And we know that's true because log base a of a is 1, and of course doesn't matter what 3x is, really doesn't matter. If the same thing that's here is here, then we know that the result has to be 1. Because this is just like saying 3x, all that raised to the power of 1 is just 3x. That's essentially another way of translating a. Similar for example B, we have log of base 9y evaluated at 9y quantity raised to the 5th. And we know that the answer to that is 5 for the same reasons here. Okay. For example C, we know that log base 13 of 13 raised to the -10 is -10. And again, we know that because log base a of a raised to the x is equal to x. Okay. Or put another way, we know that if we translated this in exponential form, 13 raised to the negative 10, or a raised to the power of y, is equal to x, which is 13 raised to the negative 10. Okay? So for example D, we see that we have 2 raised to the exponent of log base 5 of 25. Okay? And if you recall, log base 5 of 25, we know it's just a fancy way of expressing the exponent of an exponential function. In particular, the exponent that satisfies this particular equation. Give me the exponential number for an expression that has a base of 5, and the result is 25. And of course, we know the answer that goes in the box here is 2, and that's why this answer is the way that it is here. If we remember that 25 is just 5 squared, and then use property 7 to pull that out, and then just say 5 times log base 5 of 5 is 1, which ends up being 5. We can do it that way. Or an easier way to do it is just to come up here and remember that log base a of a raised to the x is just x. So log base 5 of 5 raised to the 2 is just 2. So you can do it all those different ways. So saying all that to say is that we know log base 5 of 25 is just 2, and we know that 2 squared is 4, so 4 is our final answer there. Okay. So moving on to our last set of examples here. Here we want to note that log base 2 of 8 can be rewritten as log base 2 of 2 raised to the 3, because 2 raised to the third power is 8. And from property 3, we know that log base 2 of 2 raised to the 3 is just 3. So from that point, we know that 4 raised to the log base 2 of 8 is just going to be the same as 4 raised to the third power, which is 64. Because 4 times 4 is 16. 16 times 4 is 64. Okay. For example F, we know that log of anything evaluated at 1 is 0. Okay. And so, of course, our property tells us that. So here we have log base 8 of 1. Since it's log of anything rate evaluated at 1, the answer will be 0. And again, it is because of this particular logarithmic property. And so with this example, this concludes our study on logarithmic properties and how to use them to be able to evaluate logarithmic expressions, as well as expand and contract logarithmic expressions.